Okay, let's move towards next slide. So the first question is the hydraulic retention time of the system is how many hours? So as you know, there are two types of retention time. One is hydraulic retention time, which talks about water, and the other is solid retention time. Okay, that talks about the biomass. So when we say hydraulic, it's all about water. You don't have to take care of any MLSs or the biomass present in the system. Here you need to talk about just the shape, size, and the water. So please, this is a big hint. You try to solve this question. And when we say solid retention time, we have to take care of the biomass. Solid retention time means for how much time a biomass is present inside the system. So that will be always in days, and hydraulic is in hours. If you know the answer, you can type in the chat box. We'll see the solution. As I have told you, it talks about just the design of the system as well as water. So this is our answer. This theta represents hydraulic retention time. Okay, so theta will be volume by flow rate. So what was the volume? Volume is 500 meter cube, and what is the flow rate? 3 mld. 3 mld means 3 million liters per day. So when we will put this like this, I think there is some mistake in the solution. I'll look into it, and you also try to do. Take care of the units. Volume is 5,000, 500 meter cube, right? And this is 3 mld. So we can say 3 million liters. So 3 into 10 raised to power 3 meter cube per day. I think this will be the solution. Okay, this will give in days, then we can convert it into hours. Or if this is given in average. Okay, so this will be your solution. Please correct it. Coming towards next question, here we are talking about solid retention time. As I was already discussing, it is given in days. So here we have a well derived formula for that. So you might have prepared notes for the course. So please use those notes and try to find out the solid retention time of the system. What is solid retention time? Or I'll give you the difference. When we say hydraulic retention time, we talk about a particle of water moving from this end to this end. But when we say solid retention time, we talk about a biomass which is moving from this system to this system. Just because in ASP we have some return option, something will come back. So the retention time increases for that particular bacteria. That is why it is in days. So that is what we call solid retention time. So try to answer this question. Use the formula that has been provided to you and answer the question. Please take care of the units, and the formula is little big, so try to solve properly. Use calculators. Okay, we'll see the solution now. So I'll clear it so that you can see. Okay, so theta c, which represents solid retention time, is equal to volume into xt xr plus q minus qw xc. So this is going, this is the MLSS going in the effluent. Usually we neglect this we take as 0, because what was given in the question? That suspended solid in effluent is negligible. That's why Xc we are taking as 0. Okay, that's why Xc is equal to 0. So we are left with by V into Xt upon Qw into Xr. If it is given that Xt, the outgoing concentration or outgoing suspended solid is not equal to 0, then you have to consider this whole equation. Then you have to do it very properly. So here it is nicely solved. Okay, I hope you understood. Here there is problem with V. I'll check it. Maybe when I'll upload the solutions, then I'll correct it. In the question it's giving 500 meter cube, or am I seeing it wrong? Yeah, it's giving 500 meter cube, or yeah, I don't see any other thing here. So we'll correct it. While uploading the solution, I'll correct this thing. So this is how you solve solid retention time. So if possible, if you are solving, then please take volume as 500 meter cube and give me the correct answer. Coming to the next question, activated sludge is the, we have to select the most appropriate option. So this question contains just one option. Try to answer this question. This is a theoretical question, and based on understanding you can easily solve this question if you have studied this week's lecture properly. Okay, we'll see the solution. We have to select the most appropriate option. Okay,
That is C.
yes, answer is very correct. Sludge in the secondary tank after aeration and rich in microbial mass. Option A is also correct, but option C is giving us more information. And as I have told you, there is one option correct. So the option which is giving us more information should be considered as the correct option. Okay, those who have thought answer is A, it's very, very correct. Okay, but option C is more correct. Okay, let's move towards next question. The flow sheet of liquid stream of sewage treatment scheme consists of. Here you have to give the correct sequence. So try to solve this question. Here we are talking about the liquid stream. If we would have talked about the sludge stream, then this thing would have been entirely different. The sequence would have been entirely different. So here we are talking about the liquid stream. So please try to solve this question. And if possible, if you have any idea, mention in the chat box the sequence that we can consider, or not sequence, the option that we can consider for the sludge stream, not liquid but sludge. So after biological and primary settling, after grid chamber, what will happen to the sludge? So that will be a good exercise for you. If you are not well aware how what to do with that sludge, try to find out the answer and answer me in the next session. What we can do with the sludge. And the
The answer is C. That 4, 3,
okay,
2.
1 5. Yeah, we'll see. Yes, your answer is very correct. For liquid stream, it will go like this. First, screen chamber will be there. What screen chamber will do? It will screen out the big particles like if there is food packet, papers, all those things. It will log. It will remove this thing. Third is grid chamber. What grid chamber will do? It will remove the inorganic particles. Next is primary settling tank. Uh, could you please turn off your mic? Thank you so much. Next is primary settling tank. Here we remove rest of the inorganic particles and discrete organic particles. Next comes the biological treatment. Here we try to remove all the soluble organic particles. Here bacteria is involved. After that, to separate the biomass from the supernatant from the liquid, we go for secondary settling tank. Okay, so this is the sequence in which it works. So what I was saying, try to answer the question in terms of a sludge treatment. Everywhere sludge will come, right? In the grid chamber, inorganic sludge will be there. In primary settling tank, some sludge will be there. So what can be the treatment scheme for the sludge? Try to find out the answer. You can answer me in the next session. Let's move towards the next question. Consider a wastewater plant set up in the city X. X is the name of the city. We are talking about a wastewater plant. Here we know the elevation of the city, annual average design temperature. This is a big question. Try to be very cautious with the units. Okay. Standard oxygen transfer rate we have alpha, beta, all those things. CS20 means saturation oxygen at 20 degrees Celsius. Saturation concentration at wastewater temperature and elevation H we also have 9.53 given, so you don't have to use all these above information to find out the saturation at 17 at all this height and temperature. At 17 it will be 18. Pressure at full depth of air release, atmospheric pressure, it should be written like this in the subscript. Percentage oxygen in air leaving water we have, concentration of dissolved oxygen in wastewater with Cl, Okay, calculate the average oxygen transfer rate in kg O2 per hour in the aeration tank. We are talking about the oxygen transfer rate. So there are many ways by which we can increase the oxygen content. This aeration tank is very big now. So there are many ways by which we can increase the oxygen content in the aeration tank, because biological activity is going on and the bacteria that we put there are aerobic, and aerobic bacteria needs oxygen. So there are many ways. Either we can use the mechanical aerators. Mechanical aerator means we will put an aerator which will move and provide the oxygen from the surface. Oxygen from the surface will move inside. Other thing that can be given is diffused aerator. So there will be a pipe system. Okay, there will be a pipe system. So there will be small holes in that pipe system, and oxygen will come from below. So this is what we call diffused aeration system. So these are the various ways by which we can provide oxygen. So in this question you have to calculate the average oxygen transfer rate. Okay. So you have the formula. Just try to put all the numbers and try to understand the question, what it is trying to say, what kind of system is this, how to change the values, because oxygen will change with temperature, oxygen saturation will change with temperature, right? So take care of that. Anyway, CSTH value is given to you, so you have to use this value only, but saturation should be also given, it should also be used in the formula. Please try to solve this question. I'll give you a minute to do this, or note down the data and try to solve. I hope you might have noted down the values and would have start solving the question. So let's see if the answers you're solving is matching. So this is the way by which we will calculate the oxygen transfer rate. So first of all, we have to calculate the average. Okay. So this will be calculated by this formula. What is this OT? This OT is given percentage oxygen air leaving the water. What is this 21? This is what means we will pump the air, and in air only 21% oxygen will be there. Okay, so that is why this 21%, and from this 21% only 19% is leaving the water. So that is OT we will keep here. So that is how. So effectively we are putting 21%, 19% is leaving the water. So rest the remaining percentage is getting inside the water. So that is what is required. So considering all those things, we have to calculate the rate. Okay. So this is the formula. Please go through it properly, and if you have any doubt, you just tell me. We'll see it. Please go through this properly. I will share this sheet with you, but it will be better if you can go through it now. Okay. Okay. We'll move further. So the question number 9 is also a numerical question. Please note down the values. A wastewater plant has 2700 milligram per liter mlvss. So X in the aeration tank. If the primary effluent has a BOD of 225 and the flow of 10 mld, we have the tank volume as 2000 meter cube, then the food by biomass ratio is. Okay, this you have to solve. Food by biomass ratio. Please think about the question and try to solve this. Here food is the substrate, means BOD, and biomass is the ml basis. So it's not direct. It's not like that you will divide 225 by 2700. You have to take care of the units as all those things, and this will be in terms of absolute numbers. So try to solve this question. This was pretty easy question. I hope you might have noted down the values and solved it. So when we say completely mixed aeration tank and suspended solid are a substrate around entire system, this is what we will get. Here also, what will happen? The substrate or suspended solid leaving the system, that is Xe, should be considered as negligible. Then we will get this equation. Q by Q into S naught. Q is your this flow in MLD. 1000 is the multiplication. It is in MLD. This will convert it into meter cube. After converting it to meter cube, we will multiply by S naught. That is 225 mg per liter. I told you food is BOD and biomass is ml basis. And 2000 into 2700. This will be V into X. So this is what we get, food by biomass ratio. Coming to our next question, it is a theoretical question. So it's of course easy to answer, no numericals. Now numericals are done for the week. We have done too many numericals, so please practice them very properly. And in case of any doubt, we can discuss in the next session. So now one or two theoretical questions will be there. After that, we'll wrap up. Select the major nutrient required for biological treatment. Here we are talking about the major nutrients. All of these things are required, but what is majorly required for the biological treatment? Please answer this question.
That is the nitrogen and
Yes, very correct. So the answer is nitrogen and phosphorus. Why this is majorly required? Because the bacteria or any microorganisms consume nitrogen and phosphorus. Actually, the bacteria's body, okay, yeah, bacteria's, I was saying there was some connectivity issue, I guess. So bacteria's body is made of many nutrients. It's made of carbon, hydrogen, nitrogen, phosphorus, everything. So whatever the nutrient the bacteria consumes, first it uses is for making its body, it's for its growth, and second, it uses it for the metabolic activities. So the most consumed nutrients is nitrogen and phosphorus. Okay, sulfur is also there, but it sulfur concentration is very less in its body in comparison to nitrogen and phosphorus. even for any biological treatment, either if we are using bacteria or if we are using algae, nitrogen and phosphorus will be more consumed. Let's move towards next question. The efficiency of a sedimentation tank does not depend upon, does not. Here we are talking about the sedimentation tank efficiency.
That is a big depth of tank. It is
Okay.
big
So
depth.
answer is very correct. Depth of the tank. So last time when we were discussing, I asked a question that how the efficiency of the sedimentation tank can be increased by increasing the surface area. We are increasing the surface area. Okay, I'll draw the diagram. Surface area, I am keeping the surface area same, but I want to increase the efficiency. What I can do with this depth to increase the surface efficiency? What I can do? I want to keep the surface area same. I don't want to use any more space. How do I increase the surface area without actually increasing the surface area? This will increase the efficiency of the surface tank, of the sedimentation tank. What can be the relevant options that we can go for to increase the efficiency?
Tube settlers, no?
Yes, very correct. So we are actually increasing the surface area. We are using various settlers. We are providing more surface, okay, so that the biomass can grow. So in this way, we are utilizing the height to increase the surface area. So that's all for today. Please practice properly all the numericals. All the numericals are very important. Even in this section, in this class, even in the last class there was numerical regarding the velocity. That was also very important. Please practice them as much as possible. You can use some good books. Okay. PV row you can use. I'll give you the name. Okay. This book you can use, and it's very good book for solving the numericals as well as for developing the concept. So these things you can use, and in case of any doubt you can ask me in the next class. Okay, and please do solve the numerical properly. Any doubt for now? Shall we close the session?
Okay, thank you, ma'am.
Okay, thank you everyone.
Okay, thank you.